Hi, this is Angela Galloway, and this is a lecture video for STA220. We are in section 9.2, so we are getting towards the end of our chapters here. I just did a video on 9.1. I think I had two videos for that. In 9.1, we were looking at creating confidence intervals for population proportion. So we were using p hat and p. So the next thing we're going to talk about is doing the same thing for population means. So now we're dealing with x bar and mu. Okay, so thinking back to what we learned in 9.1, we learned what a point estimate was, right? A point estimate really is what we've kind of called our statistic up to this point. So our point estimate is just one point on the line that we're using to estimate what the true parameter is. So back in 9.1, we were using p hat as an estimate for p. Here we're going to be using x bar as an estimate for mu. Okay, so we're going to create a confidence interval allowing for that margin of error, which is just our sampling error, right? Just the fact that we're taking a sample to infer something about the population. So since I couldn't get data from the entire population, I took a sample. That sample is going to have some sampling error, right? Because it's not going to be exactly like the population. So in class, what I do with my lecture class is I do this restaurant example where I have all my students, I give them a list of 125 different restaurants. They randomly choose 16 of those, and then we all calculate sample means. So this here, I know it's not the best writing because all the students wrote in their own, so it's kind of messy. But these were all our different X bars, okay? So looking at all these sample means, what we would do is, that can help us to figure out what the true mu is. So seeing where they all center, where they all center around can give us a good idea of where the true mu is. So looking at all these numbers, you might say the true mu is maybe around 900 or 950. It looks like somewhere in there, right? Then I told the class that on the next slide, this is actually the true mu of the data that I had given them. Okay, so I only knew that because I created the data myself. In most cases, we're not going to know the true mu, right? That's what we're trying to estimate. But so we knew that. So we saw that most of these fell around 911,000. But again, remember, they're just one point on the line. So when I get one X bar, I don't know how close my X bar really is to the true mu, right? It's just somewhere, hopefully in this area. This is where 95% of our X bars are going to be, right? Based on the empirical rule. But I don't know exactly what the true mu is. I'm just hoping that my X bar estimates it pretty well. So the next thing we would do is create a confidence interval. We're going to create confidence intervals for mu right now, similar to how we did for proportions. We're going to use our Z alpha half here. I'm going to do a 95%, so that's why I'm using the 1.96. This is the standard deviation of the sampling distribution, right? That's the same thing we used in section 1. We used the square root of p times 1 minus p over n, right? That was the sampling distribution's standard deviation. And then we replaced p hat for p because we said we wouldn't know the true p, right? But this again is our standard deviation of the sampling distribution. So sigma over the square root of n. So I gave the students the sigma here, 264,000. The sample size, they took samples of size 16. And then we created these confidence intervals, okay? Now what we saw was that if this was the true mean, we were looking for how many of our intervals didn't contain the true mu, okay? And so when we look through all of these, only 2 of them didn't contain the true mu. The rest of them did, okay? So the X bar, the point estimate that we got, could have been higher or lower than the true mu. But when we created the interval, almost all of these intervals did contain the true mu. Now, if we were doing 95% confidence intervals, we were saying that, 95% of them should include the true mu, and about 5% of them won't, right? So we're hoping that, when we go out and do a survey, that when we get our statistic, it's hopefully going to be one of those good ones that predicts fairly well, that's within 2 standard deviations of the mean versus one that's not. And we have a higher likelihood of getting one of those better stats than not. Okay, so that's what this whole slide is about. And this is looking at, where most of our data fell, but we did occasionally have a high one or a low one that when we created our confidence interval didn't contain that true mu. But all the statistics that fell within that 1.96 standard deviations from the mean, that interval is going to contain the true mu, okay? All right, so you may have noticed, when we were creating this confidence interval here, we use sigma over the square root of n because that is the standard deviation of the sampling distribution of x bar, right? We learned that back in chapter 8. But there's a little problem with that. With sigma, if we're trying to estimate what the true mean is, how are we going to know the standard deviation of the population? So how are we going to know this sigma? Well, the quick answer is we won't know it, right? The only way you can calculate sigma from the population is to have mu from the population, right? It's in the actual formula. So how would we be able to even create this confidence interval without knowing what sigma is? Well, there's 2 different ways you can go about that. One way is that we could just guess that what the true sigma is. So maybe we can look at another study or another population that's similar to the one we're dealing with and kind of use the sigma from there. But most of the time, what we're going to do is we're going to use something in place of sigma, okay? So instead of using sigma, we're going to use S. Okay, so we're going to use the sample standard deviation. Now we can get that, right, because we're calculating data, we're calculating an X bar, and then we could also calculate the S, the sample standard deviation. So that's fine. So now we've got X bar and S. We're going to replace S in that sigma over the square root of n. So now that's going to be what we use for our confidence interval. But now that brings up another issue. If we're thinking about our sample sizes, okay, so let's say I take a sample of size 2, or I take a sample of size 20, or I take a sample of size 200. When I look at all those different samples, which one is going to vary more? The sample of size 2 or the sample of size 200? Well, the sample of size 2 is going to vary more, right? Because now I'm just looking at 2 individuals. Once I look at 200 individuals, I start to get less variation there because I've got more people included in my study. Well, that's different than when I'm looking at the normal distribution. The normal distribution does not change based on your sample size. The normal distribution always looks like a normal distribution if that distribution is normal. But if we're saying that S depends on your sample size, then we're going to see different distributions for each sample size, okay? And because of that, we have to actually use a different distribution when we're doing these confidence intervals for mu. So because I'm using S in place of sigma, and because S depends on sample size, because the larger the sample size, the less variation there is, then I'm going to use something called the t-distribution. Now the t-distribution is kind of an interesting distribution, and this down here, if you have time, I would say you can watch this little video here. What this video goes over is how the t-distribution was created. And basically just the short version is, it's a fairly short video, but a shorter version is that back in the late 1800s, early 1900s, beer production was becoming highly competitive, okay? And the Guinness Company had started to hire biochemists to come into their factory and figure out how to make their beer as good as possible. So basically what they were doing is quality control. They were making sure that one batch tasted just like all the other batches. You know, they didn't want one batch that was good and one that was just okay and whatever, right? So a lot of the things we do today, you know, to keep up with quality control, but this was kind of a new thing that people were starting to do in the early 1900s. So they get these biochemists in, and one of the biochemists' name was William Gossett. And so he was working at Guinness, and they were looking at barley. They were taking samples of barley and figuring out, I don't know, the consistency or weight or something of the barley, okay? But he was noticing that when he was creating confidence intervals for this barley, that then when he would go back and look at it, the values was getting were not falling in his confidence interval, which meant that his confidence interval didn't seem to be, you know, 95% confident or whatever, because it seemed like more often than not, he was not getting values that fell where he thought they should. Okay. So he started to wonder if maybe it was because he was taking such small sample sizes, because when he was doing this barley stuff, these were fairly small sample sizes. And he realized that the smaller your sample size, the larger your variation. And so it wasn't really looking like a normal distribution anymore. It was looking like something else. And so he created this t-distribution. Now, when he created it, you know, in math, most of the time, if you come up with a theorem or an equation or something, you usually name it after yourself, right? So you would think this might be called the Gossett distribution or something. But when he went to publish the paper, Guinness actually said, you know, you can publish it, but you can't use your name, because if you use your name, everybody's going to know that here at Guinness, we're using biochemists to figure out how to make beer as good as you can, and we don't want other people to know that we're doing that. So he had to publish it under another name, and he just used the name student. So that's why it's called the student's tea distribution. So it did come from, you know, a real life situation, and it's still used today when you're doing quality control for very small sample sizes. Now, the thing about the t-distribution is, as our sample size gets bigger, the t-distribution starts to look like the normal distribution. So some people kind of just ignore the t-distribution and will just kind of go straight to the normal as long as they have a large enough sample size. However, your book is more cautious and always uses the t-distribution for sample means. Okay, so if we're dealing with x bar and mu, we're going to use the t-distribution. For proportions, we'll use the normal. Okay, now this is what the normal and the t-distributions look like. So you can see here how the t-distribution has much wider area, or much more area in the tails than what the typical normal distribution does. And so that's kind of the difference there. It's flatter, and the data, you know, you don't have 95% of the data within 2 standard deviations, basically, because you've got more data out here in the tails. The normal distribution, or the t-distribution, has something a little different that we don't talk about in the normal distribution, and that's the degrees of freedom. So because the normal or the t-distribution is based off a sample size, we have to have something to talk about, you know, what is our sample size. So the degrees of freedom references that. The degrees of freedom is just n minus 1, so you take your sample size and subtract 1. So here, a t-distribution of 1, that means that you actually have 2 in your sample. This one of 5 has 6 in the sample, 20 has 21, etc. So you see that when you only take 2 at a time in your sample, you know, you've got a lot more variability. So a lot more observations are going to fall out here in the tails. As you get up to 30, 100, 1,000, your t-distribution starts to look almost exactly like the z, or like the normal distribution. So since we're doing a new distribution, we have a new chart. This is our t-distribution chart. Notice what it's showing us is the area in the right tail. We called that alpha back in chapter 8, or I guess chapter 7. We talked about alpha some. We also talked about, our alpha half as we were working with confidence intervals in 9.1. So these are all the possible areas that we're going to be dealing with, the alphas or alpha halves that we're looking at. These are our degrees of freedom, so based on our sample size. And then inside here are the actual t statistics, okay, the t values. So if I just need to find the t value where the area in the right tail is 0.005 and it has 10 degrees of freedom, I'll go to the 10 row and the 0.005 column, and I'll use a 3.169. So that would be, what I would use instead of my Z alpha half. This would be like my T alpha half, okay? And this again here, there's another one. Now you notice on this chart, if you go down to the bottom, there's a row that says Z, okay? So we've got our sample sizes here, our degrees of freedom. It goes up to 100, then jumps to 1,000, and then it goes to Z. So what this is telling us is, after 1,000, the numbers start to look almost identical to what we would have in the normal distribution, okay? And really, even after like, let's see, even up here at like 100, they're fairly close to what the Z is, okay? So we know the Z alpha half for a 95% confidence interval is 1.96, right? So the T alpha half for a 95% confidence interval, if you have 1,000 people, is 1.962. Okay, almost identical, so it's going to make very little difference. Or what if you go up to, let's say we only have 40 people, then it's at 2.021. Incoming. So we can use this, these t intervals, or I'm sorry, the t chart to kind of see how these values are eventually getting very close to the z. Okay, so that's why I think some books and maybe if you look at other like YouTube videos or other instructions on how to make confidence intervals for mu. Sometimes they're going to tell you just to use the Z, but our book, we are always going to use the T, so I don't want you to be confused with that. But what you will see is that, if you've got a large sample size, the T and the Z are going to be pretty similar. Like let's say we just have 50, okay? If we had 50 or 51 people, 50 degrees of freedom, our our T statistic here is going to be 2.009 versus a Z of 1.96. Is that going to make a huge difference? Well, not really, okay? But for it to be correct in your homework, you really need to use the T, okay? So some properties of the t-distribution, it's going to basically look somewhat like a normal distribution. You've just got more area over here in the tail, so it's kind of less, I guess, less bell-shaped, I guess, more wider over there on the side. This is going to be our actual confidence interval formula for the lower and the upper bound. So we're going to have our x bar plus or minus the t alpha half, so that comes from our chart. That's based on the degrees of freedom. Then we plug in the S and then over the square root of n, okay? All right, so let's look at an example. A sample of 101 adult body temperatures showed a mean temperature of 98.2 degrees, a standard deviation of 0.62. Let's create a 95% confidence interval. And then what does that say about the common belief that 98.6 degrees is the mean body temperature? Okay, so we could do this by looking at our chart. Let's go ahead and find the T just in case you need this for anything else on your homework. If you wanted to do this one by hand, looking this up on the chart, so we had 101 people, so that'd be 100 degrees of freedom. We're doing a 95% confidence interval, so 1.984 would be the T statistic, our T alpha half, because the 0.025, that's how much is going to be in the right tail, right? Because if we're doing 95% in the middle, you have 2.5% on both sides. So that's where that comes from. So we would use 1.984. We'd multiply it times the 0.62 divided by the square root of 101, and then add and subtract that to 98.2. The other way we can do it, which is in our calculator, which is probably the way most of you would prefer, is just by doing the t-interval. So remember, for proportions, we did the one proportion z interval. For means, we're going to do the t-interval. Okay, so we go to stat and test, go down here to the t-interval. Okay, there are two options here. You can put in your data or you can put in your stats. Most of the time, the way our problems are set up, you're going to have stats and not the original data. But if for some reason you have an example where they give you a whole list of data and you're supposed to calculate the mean and the standard deviation, you can put in your data like in a list, and then it will calculate the mean and the standard deviation for you and use that to come up with your interval. But we are going to use the stats here. You're going to put in your X bar, your S, N is 101, our confidence interval is 95%, and then we're going to calculate. So there's our t-interval. So that's our lower bound and our upper bound. It's our mean and our standard deviation. So we use that t-interval on our calculator to get the t-interval here, our lower and upper bound. It gives you the mean, so you can just double check and make sure it's the same as the one you thought you typed in, the standard deviation in your sample size, and so that would be the answer. And then this one asks a little further. It says, what would this interval tell us about the belief that 98.6 is the mean body temperature? Well, because this entire interval is below 98.6, then that would make us believe that maybe 98.6 is not the true body temperature. So there's basically two possibilities. We just happened to get a sample that had a really low X bar, okay, which is possible. We have that 5% chance that we have a really low sample or a really high sample. Or this is not really the true mean temperature of everybody. Okay, so those are kind of our two options. Here's the calculator instructions if you need that to do the t-interval. And then we just have a few more examples of how to do the t-interval. I have an example from the book, and looking at this, what some students sometimes wonder is, when you get to the test, when we get to the test, it's not necessarily going to say, okay, this is, a 9.1 type problem, or this is a 9.2 problem. So you need to know how to be able to identify, are we talking about confidence intervals for means or confidence intervals for proportions, okay? So there's two things you want to look for. When we're talking about means, they're going to give you a standard deviation, okay, because we need that for the formula. They're also probably going to say mean or average somewhere. When we're talking about proportions, it should say proportion, right? And then also they don't give you a standard deviation, because remember, we calculate the standard deviation by doing the square root of p hat times 1 minus p hat over n. Okay, so those are the two differences. So if you're talking about means, we're going to do the t-interval in our calculator. Okay, that's what we just talked about. So t-interval. I'm a terrible writer with my mouse here. So t-interval is what you want to do when we're talking about mu and x bar. For proportions, we're talking about z intervals. Okay, so we're going to do the one proportion z interval when we have proportions, and these would be our answers here. Okay, so those are the differences in, how you decide, is this proportions or means, because I know that can confuse students, not necessarily when they're working on 9.1 and 9.2, because, those are all either proportions or means. But once you get to the test and everything's kind of mixed in together, just making sure you can identify this is proportions and this is means. All right, so that's the end of chapter 9, and this is just 9.2, but we're finished with that. So we just have one chapter to go before the end of the semester. So if you have any questions over this chapter 9, please be sure to email me at angela.galloway@kctcs.edu, or of course you can always come by my office. I'm located in on the main campus, Building C, Room 8, which is actually the Emporium Math Lab. It's a big computer lab. My office is just in the back of that, and so you can always come by and see me. You can find my office hours listed on Blackboard. If you're having any additional problems that you need help with, maybe like a tutoring one-on-one, and you can't come during my office hours, you can always go to the Learning Center here on main campus. You can contact Jason Dooley. His email is jason.dooley, Dooley, at kctcs.edu, and schedule an appointment with him. They can tutor all levels of math, so if you need help with stats, you can go by there and do that. We also always have open math lab on Fridays from 9 to 2 here in C8, right outside my office in that computer lab. We do have open lab with tutors every Friday from 9 to 2. So if you need that help, you can come during those times as well. All right. I hope you're enjoying this chapter. And remember, we just have one chapter to go. So we're almost done. And I think you all have done a great job. All right. So keep up the good work. And I'll see you in our next video.